Okay, we have only a little bit of time to talk about TVD scheme over here. So let me motivate this by going back to our MATLAB example. Okay. So last lecture we coded up this Burgers DDT, and I want to point out there was a bug in my code yesterday. That is, I forgot to include this line. So what happens is that we reconstructed the UL, which is the solution immediately at the left of each interface, but only for I goes from 2 to n plus 1. Because initially we were dealing with a zero boundary condition, and after we switched to the periodic boundary condition, I should have added this line, basically copy the UL at the end to UL1. I didn't do that, so that was a bug. Also, when we construct the UR, we did that for 1 to n, and I should copy the UR of 1 to UR of n to make it periodic. Okay, so that was the bug I neglected yesterday. So you can see all the bugs come from boundary conditions. So that's where it's extremely easy to introduce bugs. And if you look at a real PDE solver, especially for complex geometry, how many lines of code do you think? How many more code do you think is used to handle boundary conditions compared to like the interior? 10 times, 20 times easily. So it's a lot of boundary conditions. I know you have a lot of you spend a lot of time dealing with boundary conditions, and that's absolutely normal. All right. So yeah, in project, the good thing about project 3 is we are trying to make the boundary conditions very easy for you, so you can focus on learning finite volume schemes. All right, so that's the code we wrote yesterday, and let's repeat what we did, and I switch back to the Burgers equation. And just to remind you the problem, let me draw initial condition that I know like how to construct how to see the problem for Burgers equation now. Let's construct the initial condition that is like this. It's almost a 1 and goes down to like 0.7 and the constant over here. Okay, so that's our initial condition. For the Burgers equation, how should the solution evolve? It should propagate towards the right. And this discontinuity is going to remain as a shockwave. And this periodic discontinuity is going to become a expansion wave. All right. Okay, so let's solve it to see how it behaves. Still need to construct my x-axis. And dt again 0.01. I'm going to do the for loop. I think I have everything now. Yeah, I also put line width equal to 3 to make it, actually let me put it black. Let me make it black so it's more visible over here. So we can see that, okay, so instead of a straight shockwave, we have something like a shockwave with a lot of non-physical oscillations. All right. And instead of an expansion wave, we also have some overshoots over here. And this part is what we don't like. And why do I say it is non-physical? It is non-physical because of what's known as the non-increasing total variation for scalar conservation laws. Okay, now we are going back to the scalar world because I want to discuss the vector system of equations for you to work on the homework. Now we are back on the scalar world, but the stuff we are going to be discussing, the oscillation avoiding scheme, is going to also apply to system of conservation laws. Okay. So if we look at a conservation law, scalar conservation law, equal to 0, what we are going to find is that if we look at the x and t diagram, what we find is that we are never going to create new extremas. So if we have an initial condition like this, so no matter if it's Burger's equation or any equation, the solution is going to follow characteristics, right? And we may have shock waves where characteristics run into, but we know like no characteristics should come from the shock waves. So there is no new characteristics generating in the solution anywhere, right? Whichever characteristic line that exists at a particular time, it should already have existed at t equal to 0, right? Do we all agree on that? No new characteristic line should be generated at any time. Okay, and we also know that solutions are constant along characteristics. What does that mean? That means whatever solution that existed, whatever solution value that existed at time t should already have existed at time 0. Okay, so if you see, let's say x and u, if we draw a solution like that at t equal to 0, and we evolve to solution u at t, and remember we get something like this. Right, we got something like this. We know it is non-physical because of what? We know it is non-physical because we have a solution at time t equal to that value, and we have a solution that is equal to that value. But we know that whatever solution value at time t has should already exist at time equal to 0. If we trace the characteristics at this point, for example, back to time 0, okay, we should find time 0 should already have that solution somewhere. But time equal to 0 don't have that solution. So this overshoot and the undershoot is created out of nowhere. It shouldn't be there. And in general, this is linked to the non-increasing total variation in the solution. The total variation of a solution means if you accumulate the absolute value of the changes over the solution, if you walk across the solution. So for example, at t equal to 0, if you walk across the solution, you see a jump over here. You take the absolute value, and as you walk across this solution, you see no change. So there is no variation here. And over here to here, there is a negative jump, but you also take the absolute value. So it's you add the absolute value of the jump onto the absolute value of the jump. This is the total variation of the solution here. Or in general, total variation is defined as the integration over space, so from left to right, of the absolute value of partial u partial x dx. I mean, of course, that only works for continuous solutions, but for discontinuous solutions, you simply add the magnitude of the jumps into this total variation. Okay, so it's the amount of change you experience over the solution in the entire space. The theorem on total variation is that for a scalar conservation law, I mean, it doesn't work for system of conservation laws, but if it works for scalar conservation law, is that the amount of total variation as you evolve the solution forward in time should not change, should not increase. Actually, it should not change if you have a continuous solution. And when you have shock waves, it should monotonically decrease, because you can have characteristics run into shock waves and disappear. You can have maximum decreasing and minimum increasing. right? Okay, so what we want to achieve to avoid this non-physical solution is to have a numerical scheme that respects that property in the discrete solution. And that's what we mean by total variation diminishing, or TVD schemes. And Godunov's theorem is a theorem that is proven by the same person who invented the Godunov scheme. It says that why? It says that if you want a total variation diminishing scheme, it is impossible for the scheme to be better than first order. I mean, that kind of justifies the Godunov scheme being a first order scheme, because you cannot do a second order scheme that is a total variation diminishing. If you construct a second order scheme that works for even advection equation, purely linear advection equation, and it is higher than first order, it cannot have a total variation diminishing property. It has to create non-physical oscillations. But there is an important assumption in that theorem. The assumption is that the scheme you construct is a linear scheme for a linear differential equation. That totally makes sense, because if you are solving a linear partial differential equation, why would you discretize the partial differential equation into a nonlinear ordinary differential equation? Right? It makes all the sense in the world that when you have a linear PDE, you discretize into a system of ODs. The system of ODs should also be linear. Okay, so that's the assumption of the Godunov theorem. If you stick to that paradigm, then any TVD scheme has to be first order. And the next lecture, we are just going to break that paradigm and tell you that if you can go to a nonlinear scheme, that is, if you are willing to discretize a linear PDE into a system of nonlinear ODEs, you can do better than first order. Actually, you can go however order you want and still have a total variation diminishing scheme. And that's our introduction of limiters, a nonlinear mechanism that is going to give you high order accuracy as well as total variation diminishing property. I will see you next Monday for that.